that as grant. So I started recording, and with all that in place, so as I told you, data is the fuel for this subject. So without the data, there is no machine learning, there is no artificial intelligence. So we couldn't actually see most of the stuff that we are experiencing right now without the data, right? So let's understand better what data is. So you all know what data is. So the network providers right now is giving around 2 GB of data for you for a day, right? So you are spending almost 2 GB of data every day. What does that actually means is, so what you consume basically every day. So when you do a chat in WhatsApp, you send some messages to your friends, you get some messages from your friends, you do all the transactions, right? So that is data. And you will go to Amazon, search for some products, you buy some of them, you don't buy some of them, you add some of them to wish list, you do all that stuff. So that is all data to the vendors. So Amazon, behind the hoods, it captures all the data and uses that data to provide better experience to the customers. So that is how they improve their business, right? So to give you a better example, if you buy something, if you're searching for a washing machine in your Amazon right now, it not only brings those kind of products, it also brings you the products related to the washing machine, like detergent will be displayed under your screen on under the main product, right? You also see some kind of napkins behind it, some kind of tablets behind it. So all the products related to the washing machine, the washing machine covers or whatever it is. So that is called as a recommendation system. How this recommendation system is happening is they're using the data that the users are feeding, right? So some user might have bought detergents along with the washing machine. So they capture the data, and for the other users, they display the same data in future. So that is how they carefully use the data and extract the information out of the data and use the data to give better experience to the users. So here is another example I would like to, you know, uh, display you. So this is a data that you do have. So data doesn't necessarily means to have some kind of valuable information in it. So let's understand information later, but let's understand how the data will be captured, right? So I have my smartwatch with me, right? It is actively working all the times, and it is capturing most of the data that I do in my day, right? So when I walk, it captures how many calories I have burnt, what is my heart rate, how many steps I have walked, how much time I have walked in a day, and how much time I was idle, how much time I have slept better. I was into a deep sleep. All that stuff will be captured by this smartwatch, or the smartwatch. It doesn't necessarily means that all that information will be useful for me, but I can extract some data out of it and use that information to make myself better. How can I make myself better? Let's suppose if I'm not feeling well on a particular day of a week, constantly, I can analyze the data that this smartwatch is capturing and use that data. I can analyze that data to understand why I'm not feeling better on a particular day. What is causing me to not feeling better on that particular day is what I can understand from the data. So data, from the data we can extract useful information. Information is something which can be used by ourselves to improvise a particular kind of stuff. It can be product, it can be a human, or it can be a personal experiences, or whatever it is. So that is what basically information is, right? So now let's see a better example of what a data is and what an information is. So I have a set of data here on Monday. I would say this is the data captured by a particular device, a medical device. Okay. So on Monday, I have walked 10,000 steps. I have burned 400 calories, and number of hours I have slept is 7.5. Exercise time is 30 minutes. Heart rate is 70. Weight is 70. Water intake is 2.5 liters on that particular day. Okay. Now, you have to understand, you have this data with you. Okay. Now, can you predict something out of this data, useful information out of this data? So it's open for you. You can unmute yourself and talk on this, but you have to tell me a useful information by analyzing this data. This is a simple data set that we do have, and you have to tell me a useful information out of this data. Just you can look at every column, every value. It is all related to your health, and we know every stuff that is placed over here. And the only thing that I would like to request you is to get some information out of this data.
This data suggests that on which day how many calories burned and how much amount of water intake and what is the weight during each and every day. So what's the progress actually in our health basically it is.
Yeah, so this is all data, right? We are talking about the data. The device captured the data, but from out of this, if you carefully analyze the number of steps that we have walked on every day of a week, you can understand that my activity is very low on Sunday, right? And my activities peak on Saturday, right? So this can be related. I mean, this is the information. So on Sundays I'm not doing well, so what can I do to make it better? So am I feeling lazy on the weekend? Am I not getting up early in the morning to do the general stuff that I do on every day of a week? So you can analyze that stuff and can improvise yourself. So that is the information. So you analyzed all the data on I mean all the steps data on every day of a week, and you got some information out of it, which is useful for you because you can improve. You know you have to improve on a particular day, and you can also figure out what are the causes that is causing this lag in the activity in yourself. So that is what basic information means. That is what I have placed over here as well. You're generally active during the weeks. So if you look at this, the number of steps that you're doing every day is very good except on Sundays. So you're not particularly active on Sundays. So what you can do, this indicates that you might need to focus more on staying active on weekends. So that is what information is. So if you don't have this data, you cannot analyze that. It goes as a normal routine every day. So if you don't capture this data, you feel like you're doing much on weekends as well. But as you have the real data, you are able to figure that out. Okay. So your heart rate also, look at this heart rate. So if you look at the heart rates, the days when you have done a good activity, the heart rate is very better. But when you look at the heart rate on Sundays, it is too high. It means like your activity is directly proportional to your heart rate. The better you walk, the better your heart rate is. The worst you walk, the worst your heart rate is, right? So that is what the information is. You can correlate different parameters that the device is captured and get information out of it. Or else you can even capture some of the information by analyzing a single column in the data that is given, right? So now I hope you understood what is the difference between the data and extracting useful information out of the data. Is this clear with everyone?
Yes.
Okay,
Yes.
right. So now we are going forward with the next slide over here. And now you have to understand what a matrix is, right? So today we are going to learn the basic mathematics stuff that is required to learn or train models. We can talk about this model, machine learning stuff, all the things later. But for today, the main focus is to understand the basic mathematics that we need to have within our mind to understand the advanced stuff that we're going to learn later. Okay. I'll carefully walk you through every step that we need to, every step that we have to go through this journey, but keep concentrated on what you're learning at that moment of time. Don't go forward in thinking if you know something else. Just keep focusing on what I suppose many of you know what a matrix is, but don't skip your focus on this stuff because you're going to learn so many stuff in this matrix as well, right? Okay, so with that in mind, let's go forward. So you know what a matrix is, right? Matrix is an arrangement of numbers or data in rows and columns. So the when you say rows, I call this as a row, right? So when I say row, I call this as a row, right? When I say column, this is the column. And can you tell me how many rows are there in this particular matrix A? How many rows are there here?
N number of rows and n number of columns.
What is that? It is m number of rows, right? So we have
Ah,
m rows here and we have n columns
Mm.
here. So that is
okay.
what a column and a row in a matrix is. So if you take a particular element, if I take this particular element, what this specifies to me? So let me mark that again. So I have this element A13, right? Sorry. So I have this element A13. What this specifies? A13. One specifies the row. It specifies the row in which that element is there. And three, the second one specifies in which column it is there, right? That is what basically Aij means. Aij specifies the first letter I indicates that it is the row. And the second J indicates in which column it is there. So if someone gave you like A45, this says that this particular element is present in fourth row and fifth column, right? That is what basically an element in a matrix means. Okay, so we all know the simple form how a matrix looks like, and we also have this stuff placed over here, which is sorry. So what is this basically means is if you look at the example below, uh, if you look at this example below, we have m is equal to 3, which is number of rows is equal to 3 and number of columns is equal to 4. A matrix with 3 rows and 4 columns looks like this, right? So you're clear till this point, right? You know what a matrix is. You know what are the rows and what are the columns in this matrix, and you can also figure out if a particular element is given with in this format. You can know in which row it is there and in which column it is there. So you're
Yes,
clear
yes,
till this point, right? So now
yes.
intuition behind this matrix is something which you have to understand. What basically a matrix intuition means is that so let's take an example. You're again capturing some particular sort of data, right? So can you treat this as a matrix? This data, can you treat this as a matrix? So you have these many number of rows here and these many number of columns here. Can you treat this as a matrix?
Yes, we can treat.
Yeah, so this is an example of a matrix. So this is an intuition of a matrix. So what matrix actually helps us is matrix is a part of mathematics which helps to simplify the jobs of analyzing and analyzing the results that we got through the experiments. Let's talk about experiments, analysis, and all that stuff later. But this kind of data will be stored in the matrix is what you have to understand. Matrix is not just numbers that is placed in braces. It represents some sort of data is what you have to understand. So that data can be anything, right? The data can be the data of your health every day, or the height, the subject wise marks of the students in a class. So let's suppose you have n number of students, A, B, C, D, E students will be there, and you have different subjects like maths, physics, chemistry, Hindi, Telugu. You can have different subjects over here and different kinds of students over here, and you can store all of this data in a matrix, right? That is how matrix intuition is. Matrix will store basically some sort of useful data. Okay, so why it has to be stored in the matrix, why we call that as matrix and all, you can understand later. But for now, the major thing that has to go into your mind is that matrix will store some sort of important data that will be used in every day of our lives. Okay, so that is what matrix basically means, and you understand the basic, I mean, the rows, columns, how a matrix looks like, and all that stuff in this particular slide. Let's go back to the next slide and understand different types of matrices we do have. Okay, so we have a square matrix. What square matrix basically specifies is rows has to be equal to the column count, right? That is what a square matrix basically is. If you look at the number of rows and columns here, what is the rows and columns here?
3 by 3.
3.
3 by
Yeah. So the number of rows and columns here is like 3 by 3. So we have 3 rows and we have 3 columns. So that so when number of rows is equal to number of columns, we say that as a square matrix. When you say row matrix, you will have only one row and the columns can be n number of columns. So you say a matrix as a row matrix if the row is equal to 1, right? And coming back to the column matrix, we say a particular matrix as column matrix when the column count is equal to 1. So here it is 3 by 1. You see the other part, which is number of columns, is 1. So we call such kind of matrices as column matrices. And what is diagonal matrix? So we call these elements as diagonal elements. In simple terms, where the column and row are equal, I and j are equal, those elements we call that as diagonal elements. So if you look at this matrix, the diagonal elements of this matrix are this one, 5, 3, 9 are the diagonal elements. So apart from the diagonal elements, if the non-diagonal elements are zeros, we call that as diagonal matrix, right? So we call these as diagonal elements and we call this as non-diagonal elements. So non-diagonal elements has to be 0 for a matrix to be a diagonal matrix. Okay. So we go back to the identity matrix now. Identity matrix says the diagonal elements has to be equal to 1. The non-diagonal elements has to be equal to 0. We call such kind of element, such kind of matrix as identity matrix. Okay. And the next thing is zero matrix. What zero matrix basically is, if all the elements in a matrix is 0, we call that as zero matrix. Okay. Now you understood all the different types of matrices, and we have n number of matrices like collinear matrix, we have parallel matrices, and all the kind of matrices are there, but the only thing that you have to mainly focus is these matrices. Okay, so these are the important matrices that you have to that you will encounter mostly when you study different kinds of machine learning models in future. Okay, and there is something which is also important. Do you know how to calculate transpose of a matrix? Anyone? Transpose of a matrix. Let's suppose A is a matrix. We denote the transpose of a matrix as A transpose.
Rows are changes into columns and columns are changes into rows. Right.
Right, that's perfect. So transpose of a matrix means the rows will become columns and columns will become rows. So this will become, when I say A transpose of this matrix, it becomes 1, 2, and 3, 4, 5, and 6, 7, 8, and 9, right? This is the transpose of this matrix. So this will become the row here, and this will become the row here, and this will become the row here. Okay, so that is what transpose of a matrix means. And we call a matrix as symmetric matrix. Remember this, it is very important. We call a matrix as symmetric matrix when A transpose is equal to A. Okay, let's take the example of this identity matrix. It is A, right? Let's call this identity matrix as A. What is the transpose of this matrix? It again becomes 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So what this means is these two, this is the A transpose, but if you look at these two matrices, they both are equal, right? So if that condition is satisfied, we call this matrix as symmetric matrix. What is that? It is called as symmetric matrix, right? So we call that as symmetric matrix. So that is something which you have to understand. So these are the important types of matrices that you have to know to further dwell into different kinds of models. As and when we need something, we can learn it at that particular point of time. But these are different matrices types that you have to know. One is square, row, column, diagonal matrix, identity matrix, zero matrix, and symmetric matrix. And you also know how to calculate the transpose of a matrix. Okay. Is this clear to everyone?
Yes, understood.
Yes.
Okay. And let's go back to the next slide. Now you understood this data separately, and you also have understood matrix separately, right? And now we are combining both of them. You know what is data, you know what is a matrix individually, but now you have to understand what a data matrix is, right? So it is simple. It's self-explanatory over here. Data matrix organizes data into rows and columns. Okay, where rows represents individual records like people, products, transactions, and columns represents attributes or dimensions. Okay, so you're going to learn few terminologies here in machine learning. Okay, so the first thing is when you see a data matrix, as I told you, matrix itself will be embedded with some useful information on anything in this world. It can be the data of the customers, it can be the marks of students, it can be the genetics of different patients who are under study on who are under investigation of a particular medicine, whatever it is. They all can be all the data can be embedded into into a data matrix. Okay, so now this is an example of data matrix. I have what is this? We have income, we have purchase date and location. So this is the data of customers who purchased a particular vehicle in a particular what do we call a store. Okay, so I mean, this is the data of the customers who have bought who have bought the cars from the from a particular store. But leaving that apart, let's understand the different terminologies in the data matrix. So we call these rows as points. Okay, so there is a lot to understand here. Just keep focusing on this. We call these as points. Points in a data. Okay, points, each row is called as a point. We are no more going to call these as rows and columns. We are going to call them as points and dimensions. Okay, so these are called as dimensions. In the world of machine learning, we are no more going to call um, the data which is arranged in the form of matrix as rows and columns. We are going to call them as points and dimensions. Dimensions can also be called as attributes. Okay, so dimensions can also be called as attributes. That's the reason it is mentioned over here as attributes or dimensions. So we call these as points, we call these as dimensions. So how do we represent this in a space? What is basically mean what space basically means is you know 1D space, right? You know 2D space, x and y axis will be there. We call that as 2D space. If there is an x, y, and z, we call that as 3D space. You're aware of that, right? Anyways, we are going to deal them later, but that is what space is. So every point can be represented in that particular space. So if I have only two dimensions, if I have only let's suppose if I have only age, so it means I have only one dimension in my data. Okay, that's how you have to say I have only one dimension in my data. If you're considering two columns, you mean to say you have two dimensions in your data. So if you have three columns, it means like you have three dimensions in your data. Okay, so let me explain you that in this way. So let me know if you are able to see my screen uh, or not. I mean, are you able to see my board over here?
Yes.
Okay.
Yeah, to see.
Okay. So you have to understand this in a better way. That's the reason I'm coming over here. So you will have one-dimensional data. Is the board visible to everyone? No.
No, no.
No. I don't know why, but okay. Background. I have to visible. Okay. I don't know. I have to see that later, but let me share my screen again and show me on the paint. So I'll just draw over here only. Let's take these two dimensions now. Okay, I'm taking two different dimensions here. One is uh, you know, the age is one of the dimensions that I would like to take, and other one is okay. So I'm taking two dimensions over here, and I'll just try to walk you through how to represent this in different dimensions of a space. Okay. So I have A's here, right? A's is one of my column, and income is one of my column. There is a reason why I'm taking only these two dimensions right now. Forget about other columns at this point of time, but let's understand and focus on these two columns. I have A's as one of my dimensions, and I have income as my other dimension. Okay, so I have 3 points over here, 3 points and two dimensions. So I have this person one whose age is 32 and his income is 50 percentage, and I have person two whose age is 29 and the income is 60 percentage, and the third person has 45 and 75,000. If I want to take two dimensions, how to represent this in a two-dimensional space is what I have to understand. So this is how I draw the two-dimension space. So this is my x-axis and this is my y-axis. Okay, and I'll just make sure I take the scale of 30, 60 and 90. Okay, and here I'll take it as 25,000, and I call this as 25k, 50k, and I'll extend this to 75k. Okay, I got this two-dimensional space now. If I have to represent these, if I have to represent these points here, how do I represent them? So 32, 50,000 falls here, right? This is one of my point. Okay, so and the other one is 29,000, 29 and 60,000. So it falls somewhere here, right? In a two-dimensional space. And other one is 45 and 75,000, and somewhere over 45 and 75,000. So I represented my data in a two-dimensional space. Okay, so this is how you represent data in a two-dimensional space. So if you have more and more points in the similar way, uh, if you have more points in the similar way, let's suppose I have some points over here, I have some points over here, I can have um, I have n number of points that can be added into this dimension. And this is the geometrical representation of the data. Understand that this is the geometrical representation of the data. So when you do any analysis, you will not do the analysis using the data matrix or the data in the tabular format. The analysis of the data always happens in the geometrical view. Okay, it helps us to understand, basically just to visualize only. To the actual analysis happens in a different way that anyways we are going to learn, but to visualize the data in a better way, in an easiest way, the geometrical representation is the best form of representation. And you also know how to represent the data uh, in an in a geometrical, in a 2D space. Right now we have to taken to only two dimensions. That is the reason you have taken only two dimensions, x and y axes. If you have three dimensions, how you have to do, you also have to consider z axis, right? And now you have to plot the diagram in a three-dimensional space. So the best example of three-dimensional space is the room, right? So if you take this, you can just visualize the room over here. At one point where the three axes merge is the point which is 0, 0, 0, right? So the floor becomes the 2D space, which is x and y axis. The floor becomes two. This is the floor, okay, of the room. So the floor will be x and y axis, and the walls that are extending out of this 2D axis. So this is your ceiling of your room, and this is your room, right? Um, so this is x-axis, and this is y-axis, and this height. What is this? This height is the z-axis. So if you have points in the t-dimensional space, you can represent it in this way. So if you have three-dimensional space, the points lie in the room somewhere in middle of the room, if that is a 3D space. Just try to visualize that. So you can, the points actually lies in the room itself, somewhere floating in the room. If it is in the two-dimensional space, they will be residing on the floor of the room. If it is one-dimensional space, if I have only one dimension in my space, so it becomes a single line, and on this line you can represent those points like 0, and this is 10, 20, 30, 40, and 50. So 32 falls here, so this is one of my point. 29, this is one of my point. And 45, this is one of my point, right? So this is how you represent uh, the data if it is one dimension in a geometrical view. So you understood few terminologies here. One is the points. Points means each row in the data matrix is called as a point, and the rows, the columns in the data matrix is called as attributes or dimensions. And you also understood how to represent the data in a in geometrical view. If it is, you have seen what is one dimensional space, and you have seen what is two dimensional space, and you also have seen what is three dimensional space. Okay. um, is this clear, or are you feeling difficulty to
Is clear.
clear, right?
Uh,
So
Understood.
never just forget about these variables. Okay, we call them as categorical variables, but we also going to study about different types of variables in our next slide. But leave about this and don't even think about how to represent them in geometrical view. So basically, we have different methodologies to convert the categorical data into uh, numbers or numericals. We call that as one hot encoding. But as I told you, let's go step by step, and let's focus on what I'm saying. Anyways, you're going to learn everything one after the other. But right now, your main focus is to understand what is data matrix. And this is the example that should be in your mind. And in a data matrix, in a data matrix, you have to know what we call them as points, what we call them as dimensions, and how to represent these points in different spaces, whether it is 1D, 2D, or 3D. So that is what that those are all the takeaways from this particular slide. That's all what it is. If you're clear with everything till this point, we can go to the next slide. I just need heads up from every one of you, and it's good if it's good that if everyone is on cameras, I can just see you as well. So it would be better two-way communication. Okay, so that's that's what data matrix basically means. Okay, so is this clear, or do this needs another round of explanation? Just Clear?
Yes.
Yes, it is clear.
Okay.
Yes, understood.
Okay. So next, going back to the next slide. So we are going to learn about type of attributes now. Till this point, you have seen data matrix, right? Now you're going to understand what are different types of attributes in a particular data matrix. So this is the um, same kind of matrix taken from the previous slide, but I have added few dimensions to this particular matrix. So when I say few dimensions, you should understand I have added few more columns to that particular uh, particular matrix which you have seen before. Now let's go one after the other. Okay, so look at this. Look at concentrate only on this particular dimension now. So look at this dimension. So we call these as categorical variables. So if you are seeing something which is not a numerical number, we call that as a categorical variable. Okay. So these two falls under categorical variables. So we can also call them as qualitative variables. Okay. There are two words to this: categorical variable or qualitative variable. And there is another type called as quantitative variable. Quantity itself says it is related to something called some kind of numericals, quantity, right? So these are categorical variables. Inside the categorical variables can be subdivided into two types. One is nominal variable, other one is ordinal variables. Okay, so types of attributes I have said. It can also be said as types of dimensions or attributes, whatever it is up to you. And there are also different terminologies that we will learn now, but let's understand different types of attributes or dimensions. So the first category is categorical variables. Categorical variables can be subdivided into two types. One is nominal and the other one is ordinal. So what is the difference between nominal and ordinal is, so for nominal variables, we don't have any defined order. Look at this. We don't have any defined order. Let's suppose I have names, John, Alice, Bob. Is there any relation between these variables? So they are independent, right? So names are independent. Um, so such kind of variables which are independent of itself, like they don't have any order. They will not have any defined orders, and they act like independent values. So such kind of variables are called as nominal variables. Okay, and variables which have defined order. Okay, if you look at these variables, low, medium, and high. So if someone asks you to order them, you order them as low, medium, and high, right? So there is a feasibility to maintain some order with the values of those variables. So such kind of variables are called as ordinal variables. If you couldn't actually keep those variables in a particular order, if you cannot maintain any order for those variables, and if you went into some kind of state of not able to do that particular thing with the variables that are given, such kind of variables are called as nominal variables. Okay, so if you take another example for the ordinal variables, let's take your education. You study higher education, and then you do your bachelor's, and then you do your master's, right? So they can be ordered. So the first comes the high school, the second comes the bachelor's, and the third comes the master's, right? So they can be ordered. Such kind of variables are called as ordinal variables. And the variables which cannot be placed in an order, or they don't have any defined order, are called as nominal variables. So those are two different kinds of variables under categorical variables or categorical attributes. So categorical attributes can be subdivided into nominal variables and ordinal variables. Nominal variables means no defined order. Ordinal variables means they will have a defined order. Okay, understood?
Yes.
Yes, understood.
Okay, please don't hesitate to stop me. The ones that we're going to discuss are the core. if you don't understand the terminologies or any kind of stuff right now, it would be easy to understand the models and to predict the models, or go to an intuition understanding of the models. But if you're clear with these concepts, it would be the next steps would be very easy. So please make sure, if you don't understand something, stop me right away. I can take another approach to explain that, but try to make sure you understand everything that you're going to that are going through right now. So
Sure.
if you don't understand something, stop me right away, and I can fetch some internet examples as well if you want, and I can also visualize the data, yeah, if you want to have that visualization. But try to make sure you understood everything that I'm saying right now. Okay, so if you want me to give you another example, good, better, best. Okay, so you can order them as well. So anything that can be ordered is, you know, ordinal variables. Anything that cannot be ordered, or they don't follow any definite order, are called as nominal variables. Okay, and now go back to the next category, which are called as numeric variables. Okay, under numeric you will have two categories. Okay, one is called as discrete, other one is called as continuous. Discrete variables means they will have a defined difference between different values in that, or they comes from a defined list. Okay, let's suppose if you take the outcomes of a die, right? If you take the outcome of a die, you all know what a dice is, right? Dice will have only
Mhm.
6 options. One is I'm not really sure, 1 2 3 4 5 6, right? You will have 6 options on the dice.
Yes.
So out of these 6 options, you cannot get the value out of these 6 options. You have defined set of values that comes into that particular category, or that falls into, if I say this particular column as dice, dice of a row, dice, uh, dice output. So dice output will be discrete values. They will not be continuous. But if you take the height of students in a class, they can be continuous, right? They cannot come out of a defined order. So some might be 5.5 feet, some might be 5.4 feet, some might be in 5.3 feet, 5.2 feet. So that integers, you see that, so those are called as continuous variables. So they can come from any, they can fall under any values between two integers. If you, to keep it simple, integers will be like discrete, falls under discrete. Continuous falls under continuous, I mean real values inside that variable. So that is what basically, there are two categories. One is categorical variables and the other one is numerical variables. Under numerical variables you have two types. One is discrete, other one is continuous. What discrete means, they will come out from a defined set of values. Okay, the interval between them is defined. You can keep it short. The interval between the numbers will be defined, or meaningful. If the interval between the variables is not meaningful, or cannot be defined, such kind of variables are called as continuous variables. If you take the height of members in a class, they can be 5.55, they can be 5.56, and they can also be 5.565, right? You cannot actually predict them. They're all continuous. Okay, so they're all continuous. Any points can fall beside other point. But if you take these variables, they will have a defined set of difference between them. That is what discrete and continuous basically means. Okay, is that clear?
Yes, ma'am.
Yes.
Okay, let me just bring in okay, so these are discrete, right? So 2 4 6, this is how discrete basically looks like. Continuous means you can get values at any point. Okay, so they all comes under continuous. So this is a good example. Obtained by counting values each as integer. Okay, continuous means obtained from the data that can take infinite many values. So height of a class can take infinite many values. They cannot be like 5, 6 constant. So one cannot just be 6 feet all the times, or two persons cannot just be 6 feet all the times. So they can be 6, 6.1, 6.11, 6.12. So they can take infinite values. So such kind of values are called as continuous values. So if you take you score in this upcoming mid-exam terms, so they can come out of like from the discrete set, they can get 25.5 or 26, 27 till 100. So there is an defined set of numbers or defined set of possibilities. Such kind of values are called as discrete. The other side is called as continuous. Clear for everyone?
Yes.
Okay.
That's not.
So now the other types is, timestamp. Timestamp basically looks like date and time formats, right? This is date. When you look at something, you can simply say it is a date or it is a timestamp. Timestamp just means it will have date, time as well. Beside the date, you will also get the time. Time intervals. So this also comes under numerical variables, but this is just a subtype that is given. But basically, in our analogy, we always come across categorical variables and numerical variables. Categorical variables will be subdivided into nominal and ordinal, and integer variables will be subdivided into integers, I mean, discrete and continuous. Okay. So we call this as binary. Yes or no's, ones or zeros are called as binaries. So there is only two possibilities. When you say binary, there are only two possibilities. You can say yes or you can say no. Will you join the class? Yes or no is the answer, right? So that's how yes will be represented by 1 and no can be represented by 0. So that's an alternative conversion to numerical forms. So that is what we call as binary, and you understand what a timestamp is. You also have you also know the time intervals. You can this also falls under the numerical variables in the real world, but it's just given as time interval. And now you have to understand what is spatial variables. Spatial variables means location. The location will be defined sometimes in latitudes and longitudes, right? You know that, right? So any location can be precisely described with latitudes and longitude numbers. So such kind of variables are called as spatial variables. Locations, latitude, longitude values, all this comes under spatial values. Okay, we call them as spatial variables. So textual, any text is called as textual attribute. Multi-valued attributes means you can have multiple values inside that column. Okay, such kind of variables are called as multi-valued attributes. Okay, and this is derived. Derived means this value is derived from some set of other values. Okay, so this is 5,000 salary. This is the 5,000 salary for this person. What is his annual spend is 60,000. Let's call this as spend of that particular person. He is going to spend 50,000 in each month. So what is his annual spend is, it can be derived from this value, right? We just have to multiply with the constant, which is 12 months. So this will become the derived attribute. Okay, so such kind of attributes which can be derived from the other attributes is called as derived attributes. Okay, so we talked about categorical variables, which are of two types. One is nominal, other one is ordinal. Nominal means no specific order or no defined order. Ordinal means we will have a defined order. And the other type is numerical. Under numerical, we will have discrete, and the other one is continuous. So continuous can take infinite number of values within it, whereas discrete can take defined set of values within it, right? And the other one is binary. Binary can be just yes or no, 1 or 0. Yes will be represented by 1, no will be represented by 0. Timestamp, time intervals. Spatials are just the locations. The text, it's just the general text. and you have multi-valued. Multi-valued means you will have multiple values inside that particular attribute. Derived means, understand this, derived means you are deriving the value of this particular attribute by using the attributes that are present in the data already. So existing attributes value will be used to derive the value of the derived attributes. So those kind of attributes are called as derived attributes. So is this clear?
Yes,
Yes.
sir.
Okay. So now you have to understand one thing which is very important, which is so let me just bring up that here itself. So you're looking at this, right? So these are all attributes that you are using to derive something. Okay. So let's suppose I am deriving annual spend by using all these attributes. Okay. I am deriving this attribute by using all these attributes. Okay. So the attributes that are used to derive the derived attribute are called as features in the machine learning terminology. Okay, and we call the derived attribute as label. Okay, so understand, if you want to understand this in a better way, let me give you an example. I want to predict using a machine learning model. If I input an animal to that model, it has to say me whether it is dog or not. Okay, so that is what basically you're trying to do with the model. You have a model here, and to this model, this is dog predictor model. I call this as dog predictor. So when you give any image to this model, which is dog predictor, it has to say whether it is dog or not. It will have only two values, which is yes or no, right? So what kind of attribute is this derived variable now?
Binary.
Yeah, binary in the sense, yeah, this is of type binary, right? Because we have only yes or no in the output. Now we are sending an image. If you are sending a cat image to this predictor, what it will do is it will say no if this is working with 100% accuracy. If you're giving it as a dog, what it says yes. If you are giving line image to this predictor, it says no, right? If you're giving any animal image other than dog, it has to say no. If you're giving dog's image, it has to say yes, right? That is what this model will basically do. And now how this model will be trained, how we are training this model to predict a dog or to predict an cat, right? Or to predict not dog. So what we do is we feed that model with some features. We train that model. Understand these terminologies. We train that model with some data and we test that model with some data, right? We train the model, we test that model, and finally, once trained, what this model will do is it will predict whether that is dog or not. Okay. So now to train this model, we have to feed some features to this model. Okay. We call this, though we are calling that as features. We are feeding features to this model. We are training this model using features of the data set that we do have, and the output of this model is called as label. The label is basically it's a dog or it's not a dog, yes dog, no it's not dog. That's what the model output is. Now we have three records here. This is our data set. Inside this data set we have three records, right? Out of these three records, I cannot use all these records to train my model or to train my this to train my dog predictor model, because I have to split this data, right? I have some set of data. I have to split this data. Some data has to be used to train the model, and some data has to, uh, you know, like used to test the model because I know the answers of all those of all those records of all the data sets that we do have. If I don't know the answer, I cannot predict whether the model is performing right or not, right? Only if I know the answer for the data, I can predict whether the model is working right or not. Okay, so I'd like to make this very clear. Let's take an example and do it. Let's take the same example, dog example. Now, so what are the features of a dog? It barks, right? If you just look at the dog, it will have four legs. Is one of the features of the dog, right? It will have a tail. It is the feature of the dog. And you can tell me some other things that you remember, right? What are the
It
other?
is in color. Color.
Yeah, color can also be used. Color of the dog, and what others you
Shape
can.
and look.
Yeah, some kind of like ears are like, you know, ears will be round, nose will be pointed nose and all that stuff. Okay, so I have this data with me. So if I have dog, this is S, this is S, this is S, this is S, this is S. If I have cat, this is true, this is S, this is yes, this is
Yes.
this eyes will be different from dogs to cats. If I take lion, no, it has four legs, it will have tail, color will be different to color will also be there, but that feature will be cannot predict that in this would be a not this would not be a major feature. Okay, so we will understand what to eliminate in the features, what features has to be used, what features will give most value to train that model. We will learn all of that, and eyes will also look different for this. So now if I am feeding this particular predictor with a dog, okay, so now I'll train with only these two features. In real world, we will have around 8,000 records to train a model, and we will have some 500 records to test that model. Right now, we just have we scaled down, and now we are using these two features to train the model. So you say to this model that this these are the features has to be yes to say that that particular image is dog. If you don't have these features, say that as no. That's how we feed. So out of these variables, this is the label, right? This is the this we call as label because we are predicting this using these values. We are predicting this. That's the reason we call these as features. We call this as label. Understood? And we call the whole thing as data set. We know the output. We know the inputs. Inputs are also called as features. Output is called as label. And this whole thing is called as data set. Inside this data set, we can have different types of attributes. And this data set is divided into two things. One is training data set, and the other one is test data set. Okay. Oh, I call the other one as test data set. I call the other one as test data set. This single record, I'm calling it as test data set. Oh, sorry. So this single record, I'm calling it as test data set. Why I'm calling that as test data set? The reason why I picked that as test data set is that um, I want to know the answer, right? Without knowing how the model is performing, I cannot go ahead. So in practical world, we choose 80% of the data, 80% of records in the data set as training set, and 20% of the data as the testing set. So now I trained my model with using this data. I trained my model. So hey model, you have to understand that the image that is feeding to you has to be pointed, should have four legs, should have four tails, should have this color, should have this eyes. If all these features are matching, you just say that as a dog. If any of these are not matching to the image that is feeding to you, you have to say that as a no. Now I trained the model. Now I have to test how this model is performing, right? So if now I feed this data set, What I'll feed? I feed only this particular data. I feed only futures. I will not feed label. Label is something which has to be predicted by the model, right? Label is something which has to be predicted by the model. The only things that you feed is inputs. Inputs are called as features in machine learning terminology, right? Now you are feeding this, and now if the model says dog, you are feeding this data. But if the model says dog, what it basically means, your model is not performing well. You have to retrain that. You have to modify the algorithm that is used inside that model. That is what it says, right? So if you don't know the answer of, if you are using everything, every data that you have to train the model, okay, and in future, if you're giving the same uh, trained data as an input to predict how the model is performing, that will not work, because it already has that data, so that it can actually predict the right value. It always predicts the right value because you feed it the data already to it. I mean, you use the data to train the model, so the model is trained using that data. So it always knows the answer out of that. So that's the reason what you have to do is you have to split the data into two parts. One is testing data and the other one is training data. You train the model with the training data and use the rest of the values or rest of the records in that matrix, or in the data, or in the, I mean, in the data matrix, to predict the output of that model, how that model is performing. Okay, you know the output to this. If you don't know the output, you cannot actually testify whether the model is working fine or not. If this still says not dog, your model is performing slightly well. Okay, so that is the reason you have to split the whole data into two parts. One is training data, testing data, and you also understood what are features and what is label, and what is training set, what is training set, what is test set, and what is data matrix. So you have learned all that stuff. So don't bother about model stuff and all. What you just have to take away from this particular slide is what are different types of variables: categorical variable and numerical variable. What are different types of categorical variables? Nominal variables and ordinal variables. What does nominal means? Nominal means it doesn't have any defined order. Ordinal means it will have a defined order. So when you go to numerical, it will have two, numerical can be subdivided into two parts. One is integers, I mean, one is discrete and the other one is continuous. And you also have seen different types of attributes or dimensions. They can be binary, timestamp, time interval, or spatial, which is locations, textual, multi-valued. And coming to the machine learning terminologies, you have understood what are features, what are labels, and now you also have understood what is training set and what is test set, and what is the predominance of dividing the data into two parts: training set and test set. So that is what those are the takeaways from this particular slide. Clear
Yes.
for everyone?
Yes, Sunny.
Yes.
Okay. Now, I don't know how to get rid of this, but shit. So that is what basically you have learned 4 slides, 5 slides now, and going back to the vectors, which is very important. So let's do a small quiz for a minute. And what I request is I'll stop sharing my screen and I'll pause the recording as well for a minute. Um, so um, so this is, I call this as x-axis. Okay, on x-axis, this looks like a scale. Take the example of a scale. And if you look at the floor of your room, it is a two-dimensional space. So on two-dimensional space is nothing but if you have a stick, if you drag that stick from one side to the other side slowly, if I'm dragging this stick towards this, what you'll get, you will get some sort of plane like this, right? You'll
Mm.
get some sort of plane. So that becomes your room floor, right? That becomes your room floor. What happens? You're just focusing on x values here. So here also, this is the same line that you have dragged here, the same line you drag here. Anywhere on this point, x value will be 0 because you're dragging the same line, right? But what changes here is now this became a two-dimensional plane. So the y value will increase. So y becomes 1 here, y is 2 here, y is 3 here. So if you have to represent this particular point, this becomes x equal to 1 and y is equal to 1, right? And now if you have to represent this point, this becomes 2 comma 2. And now if you have to represent this point, this becomes 3 comma 2.
Comma 2.
First comes x and the next comes y. That is how a point will be represented in a two-dimensional space. Understood? So if you
Okay.
want to go to this point, it becomes 5 comma 3, right? So this becomes 4 comma 1 because it is 1 here. And what is the point on this y-axis? This point becomes 0 comma
Comma 2.
2. Understood? This is what two dimension means. Is this clear?
Yes.
Now leave for everyone. Okay, let me ask one after the other. So what does this point becomes, Madhu? How to
What,
represent?
Anya?
How do we represent this point in 2D?
6 comma 2.
Perfect. So Chintu,
Anya,
what do we represent?
Chintu voice is can't able to speak. Wait, I'm going.
Oh,
Chip.
who else is there?
Now
Hello.
it he is available.
Hello, Anya.
Chintu,
Uh,
how to represent this point here?
Exact 4, 5 middle. 4.5 and
Let's
2.
say it is 4.5. So what
4.5
4.5 comma
2.
2, right? So that is what a two-dimensional representation means. Now you understood what a 2D is, right? And you can represent any point on a 2D now. So what I'll do next is that I'll go to a new dimension. So now I have 2D plane with me. Okay. Now I have 2D with me. So this is my 2D. Okay. Now look at the floor of your room. You have 2D and now you look at the floor of your room. Now what you're doing is you're moving your floor to the top of your ceiling. Okay, you're moving your 2D plane upwards. So if I move this upwards, what this actually becomes is it becomes a 3D plane. So I couldn't actually represent that, but let me just give it a try to better visualize it. So this is my ceiling and this is my floor. And now I'm just moving this from the 2D space to the 3D space. Okay. So now this is my room. Now I have to figure out the points within it. Okay. I have to figure the points inside this room. Now, if you go into this room, just visualize this as a room. If you go into this room, so what is your plane? What is your floor? This is your floor, right? Let's suppose this is your floor. So this is your floor. Or I mean, this actually looks like your floor, right? So this is your floor. And these are your three walls. This is wall number 1. This is wall number 2. And this is wall number 3. And this is your ceiling of your house. Now you can represent any point on this floor, right? Which is 2D. Now it's time to represent points inside in this space inside the room. If a point is floating here, how to represent this room? So now you know this is x-axis, right? This is x-axis and this is y-axis, right? And now the third dimension is z-axis. This is z-axis. Okay. So this is z, this is x, this is y, and this is z. Z means one of your floors, this edge will
Wall.
become the z-axis.
Wall.
So now what this point becomes, it becomes 0 comma 0 comma 0,
0.
where x and y and z are 0 here. So what about this point? here x is equal to 1, right?
X
So
is 1.
just focus on the x and y. So x is 1 here, y is 0 here,
0.
and let's leave about z now. If you take this point, it is 2 comma 0 comma some value of z, right? So if z is 0 here, what z will become here? Y equal to 0 here. So here y equal to 0. Z will also be 0 here, right? And z will also be 0 over here.
Yes, because the point is
Similarly,
on X.
yeah. So if you take this point, now on the floor, on y-axis, what the value of this will be? So let's call y as 1 here. How to represent this point?
0, 1,
0, 1, 0.
0.
Right. 0, 1, 0. So what about this point?
0 to 0.
0, 2, 0. That's right. Now we understood everything of that sort. Now, if I have a point which I have to identify here, I have now my point here now on the floor somewhere at 2 comma 2, on
2,
my floor
2, 0.
somewhere on 2 comma 2. What will be the representation of that?
2,
2,
2, 0.
0.
2 comma 2 comma 0 would be my point. Now you understood that. Now move that up. What will be the value of a point here
2, 2,
on this
0,
edge?
1.
0, 0.
0 comma
0, 0, 1. Okay.
0 comma 0 comma 1, because this is horizon. Here z is
Yeah,
extending, right? Now I have my z here. I have this point, right? Now I'm moving this point up into the space. This is on my floor now. I'm extending this point to this point here now. Understood? I'm lifting this point into the space. It is floating somewhere in the room. Now, what will be the representation of this point?
2, 2, 1.
2 comma?
2, 1.
1.
Perfect. That's awesome. It's simple. Now you got the main intention, right? Now I have a point over here. Like 1, this is at 1, this is at 2. What will be the representation of it? This is floating in the space. Just remember that.
1, 0, 2.
1
2.
comma?
1, 0, 2.
0. 1, 1, 1, 2.
Perfect. 1 comma 1 comma 2. So it is point over here, which is x equal to 1, y
Okay.
equal to 1,
Y
and it
equal
is
to 1.
going up at z equal to 2. Now just go visualize this picture. Now you'll understand how does that 3D picture looks like. So if you take this diagram, look at this picture. It is floating in the space, right? What would be the value of it? So this is x, this is y, and this is z. Now tell me how to represent this point in this 3D space.
2, 3, 1.
Awesome. That's all. That is how you represent a point in a 3D space. It's 2 comma 3 comma 1, right? Now you understood that clearly. Should go back to whom I should go back to. So we have different points here. Okay. Now let's let everyone answer this one after the other. So first with this one. What this point will be now?
Which point?
What's that? What is this point here?
Where?
This point.
Oh,
4,
5.
4, minus 15.
4 comma minus 30.
4 comma minus 15 comma 0.
Why is that minus 15? Oh, you.
Actually, it is lies in between minus 10 to minus 35 in y-axis.
Okay.
So somewhat took around 15.
Okay. So now let each one answer. Let's see how others understood this, which is very important. That's the reason I'm going with each one. So, uh, Kranti,
None.
what is the geometrical representation of this? Radha,
0, 0, 33 maybe.
0, 0, 33. Perfect. Um, this is right. This is right. And now Chintu, Kranti, you can give a try with this. This is reserved for you. Chintu,
5, 40,
5,
5 comma 40 comma
10.
5, 40, 0.
5 comma 40 comma
గట్టిగా చెప్పు మళ్ళీ చెప్పు
5, 0, 9.
5 comma 0 comma 9. Apu, that's wrong.
0, 0, 9.
చింటూది
Chintu,
5, 0,
wait,
9.
wait, let him answer. Madhu, so this is done. This is done.
10.
Madhu, Kranti, Chintu.
10 comma 60 comma 50, 55 or 59. 10 comma 59 comma 0
Is that 0?
is oh sorry 4 4
Somewhere.
4 or oh my God. 10 comma 50 comma
10 comma 60 comma Chintu, Kranti.
5, 40, 0.
0, 5 comma 40 comma 0. This is right. Chintu, Madhu.
5, 9, 0.
5 comma 9 comma 0.
Wrong.
Chintu is wrong.
Madhu?
5, 0,
ఏంటడి?
This for you.
Okay. 10, 10 కాదు.
Mhm.
If I
How to represent how to represent a vector in different spaces is what you're going to learn now. Um, Going back to the slide vector. Sorry. Okay. So this is all basic mathematics that you will come to know all the times. Vector is just a mathematical object which will have magnitude and direction. Okay. A vector can be represented in various forms. So we have different types of vectors as well, but let's understand the basic vector, how to represent a basic vector in this particular slide. So you have seen the geometrical representation of that till now. Now you're going to understand about the vector notation of different points. So I have a vector. It's saying I have a vector v that starts from origin and points to the point 3, 4. So every vector, basically a vector will be represented in this way. Okay. I don't know why a vector will be represented like this. So this is the origin and this is the destination of the vector. Okay, how to represent this vector? So look at this. This is the direction of the vector. It is said that a vector has both magnitude and the direction. What is the magnitude? Magnitude is nothing but the length of this line. And direction means into to which direction this is pointing towards is the direction of the vector. It gives the magnitude and also the direction of a particular that object will have both magnitude and direction. Such kind of object is called as vector in mathematics. Now you're talking about two dimensions. So this is a point in two dimension, right? When you have x and y, it is two-dimensional point. Is that right?
Yes.
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 Now let's suppose this is my 2D point. Okay. So this is my x-axis. This is my y-axis. And this is my 0, 1, 2, 3, 4, 1, 2, 3, and 4. Right? Now I want to represent 0, 0 and 3, 4. How do you represent them? You have to represent 2, 2, 0, 0 and 3, 4. Where does 0, 0 falls? This is where 0, 0 falls, right?
Yes.
So where does 3 falls? 3 falls here. So this
3
is
on x-axis,
4 on y-axis.
4 on y-axis.
so this is my 0, 0 and this is my 3, 4, right? This is my point 3, 4. So the vector is starting at 0, 0, points to the point 3, 4. It is pointing towards 3, 4. So this becomes my vector, right? Is that right?
Yeah.
So
Son, yeah.
that is how you represent a vector. What is the magnitude of a vector? Let me call this point as x1 comma y1. So if I say magnitude of a vector, this is the formula for calculating magnitude of a vector. You are saying a magnitude will have a vector will have a magnitude and direction. Now you are trying to understand how to calculate the magnitude of a vector when 2 points are given. I'll say a vector is starting at 0, comma 0, points to the point 3, comma 4. That is what it is given. So it can be any point. It doesn't need to be 0, comma 0. It can be 1, comma 2 or 2, comma 3, whatever it is. I'll call this point as x1 comma y1, and I'll call the other point as x2 comma y2. So these are the 2 points, and my vector is starting at one point and points to a point, points to the other point, which is x2 comma y2. If I want to find out the length of this vector or magnitude of this vector, the formula is x2 minus x1 whole square plus y2 minus
X2
y1
minus
whole
Y1.
square root of. Okay. So it says x2 minus x2 minus x1 whole square plus y2 minus y1 whole square. That is the formula of finding the magnitude of an vector. Now you know what is x and y. x1 and y1 is 0, comma 0. And you also know what is x2, comma y2, which is 3, comma 4. You are going to calculate the value of this formula, which is the magnitude of the vector. Okay. So if you have to calculate that, how do you calculate? What is the x2 here? x2 is
3,
3, comma x1 is
0.
0.
0.
0 whole square plus what is y2?
4.
4 minus
4.
0 whole square.
Whole square. So 3 square becomes
9.
9,
plus 4 square becomes
16,
16. So root of 9 plus 16
25,
is 25, which is 5.
25.
So magnitude of a vector is 5. So that
5.
is what it is given over here. So that is how you calculate the magnitude of a vector. Okay. And now, and you obviously know it is given that the vector moves from 0, comma 0 to 3, comma 4. So you say that vector points from 0, comma 0 to 3, comma 4. That is the direction of the vector. So it's simply given that x square plus y square is given. But we have said that the formula is x2 minus x1 whole square plus y2 minus y1 whole square. So this is applicable for the vectors which starts from origin. So when it starts from origin, x1 becomes 0, y1 becomes 0. So the formula becomes x2 square plus y2 square. Or simply it is x square plus y square. That is why it is given like that. So the general formula is x2 minus x1 whole square plus y2 minus y1 whole square to the square root of it. Understood?
Yeah.
Okay. Now,
Yes.
now you understood the geometrical representation of the vector. So this is how you represent the vector in a geometrical representation. So starting from here, so until now you just have learned the basics which will be useful, but you will deal mostly with this stuff going forward with any of the machine learning term and understanding or any with any of the machine learning concepts. This is very important what you're going to learn. So you can also represent the vector in quadinal representation. So this is called as quadinal form. You have point 3, comma 4, right? You are representing that as in column vector which is 3, comma 4. Okay. So if you're considering a three-dimensional point, let's suppose I'm saying the point as 1, comma 2, comma 3. If you want to represent this as an in quadinal form, it becomes 1, comma 2, comma 3. It becomes a column vector. Please understand, in cardinal form, a vector will be represented as a column matrix. Okay, so that's the reason 1, comma 2, comma 3 point becomes 1, comma 2, comma 3. Okay, understood? What is the cardinal form of a particular point or a particular vector?
Yes.
Now, I'll put forward a simple question for every one of you now to understand this better. I'll go back to the data matrix now. I'm going back to the data matrix and I'm asking you a question here. So what are points here? Let's consider this as a data matrix. What are points here?
Dates.
Steps.
What are points here and what are attributes or dimensions here?
Oh, okay. Dates are points.
Dates. So this entire row will become one point.
Uh,
This
Monday, Tuesday, Wednesday
row,
is called the points.
rows are points. I told you again, rows are points and columns are dimensions. Okay. So row is a point here. So this row is a point and this column is a dimension.
Dimension.
Now, if you want to represent a point in, if you want to represent a point in cardinal form, how do you represent this point? So consider this as a vector, this point as a vector. We can represent a point as a vector or a point, you can also represent as a point. Just now you have seen, if you have a point 3 comma 2, the cardinal form of representation of this is 3 comma 2.
3, 2.
I'm saying just now we entered into learning the machine learning stuff. Okay. With vectors, we deal most of the stuff with vectors and matrix. So just now you entered into the world of machine learning basics. So understand this very clearly. You shouldn't forget what is a point and what is a dimension, because every time you do something on this field, the first step is the data. You have to understand the data. You have to know the terminologies of the data. You have to understand what is a feature, what is a label. When someone say what is, it's a nominal variable. You have to understand what is a nominal variable. Someone says it is an ordinal variable. You have to understand what is ordinal variable. You have to understand what is a numerical variable, what is a discrete, what is continuous, what is binary, what is timestamp, what is a spatial variable. You have to understand, when you heard about these terminologies, you have to automatically understand, okay, this attribute is of this kind. That knowledge has to be coming into your mind. When someone say point, you shouldn't think like what is point. You shouldn't be at that stage still. We almost spent all 1.5 hours with this. So you should cross that stage. When I say point, you have to understand what a point basically. So I'm just repeating that again. Point is nothing but this is the point. This entire row will be the point. This entire column will be the attribute or dimension or future, or it can be a label. Label is a derived stuff, right? So that part you have to actually be clear with by now. So now I say I have a point. If I want to represent that in cardinal form, how I'm doing that? I'm doing that in this way, right? This is the cardinal representation. A column matrix representation is the cardinal representation of a point. Now, if I have to represent this point, I have how many points I have here? I have 7 points here. 3, 4, 5, 6, 7 points here. And how many attributes I have here?
1, 2, 3, 4, 5, 6, 7,
8.
8.
8.
1, 2, 3, 4, 5, 6, 7, 8 attributes are there, or 8 dimensions are there. Now, if I have to represent this point in cardinal form, I am trying to represent this point in cardinal form. How do I represent it? So I represent it this way. So the first one will be Monday. So
10,000.
this
10,000.
this can be a point, or we can also, this is a point. You can represent this as in geometrical representation, or you can also represent this in vector form. When I represent this in vector form, vector can be represented in two ways. One is the geometrical way of representing it, and the other one is cardinal form. Now I'm trying to represent this in cardinal form. So if I'm trying to represent this
10,000.
in cardinal form, this is how I represent
400.
that. It looks like,
7.5.
yeah, 30, 70, whatever the values are not big matter here. So how do you represent that particular vector is something which you have to understand. So I can represent everything as a quadrenal form. Now, from now onwards, I call this as X. Okay, look at understand the terminology that we are doing it. So this, I call this cardinal form matrix or cardinal representation of a vector as X. If I say X transpose, what does this become? This become a row matrix, right? So Monday
X.
1707.5, that is what basically X transpose is. Now you are representing the points in the in the vectorial form or cardinal form of a vector. Okay, so that is what you're doing. And I already told you that, let's suppose I call this as xi. So I call this as xi or x1, x2, x3. I call this as um, xj. I mean, I can also consider as x1, x2, x3, x4. Okay, so if I have to represent this particular point, I have to say x2 and 4, right? Xij. You remember this matrix?
Hmm.
3, 2,
Yeah.
3. From now onwards, I'm changing the notation in the data matrix. If I have to represent a column, how do I represent this is xi dot. Okay, xi dot. If you look at this, I is constant, right? Sorry, this has to be changed. It is x dot j. Only j is changing, and this is remaining constant. Is that right?
Yes.
So if you look at this, how can we represent this? This can be represented as xi dot, right?
Yes.
Because
Because J is constant.
j is constant and I is changing,
Change. Very.
right? So just remember those notations. So we are saying x dot j and x I dot. So I'm going back to this form again. So you understand the cardinal vectorial representation or the cardinal form representation of this point, right? You already understood
Yes.
that. Okay. So now that is what you have to understand. Let me go back to this. Where we are now. Okay. So that is what cardinal representation of a vector is. Now this slide is done. You're all clear with it with this, right? A point can also be represented as a vector. I mean, any geometrical representation of a point can also be represented in the vector form as well. So that is what it is. So you will understand what are the usages of this vector, how do we use this vector when we analyze the data and all that stuff. You'll learn it shortly. But you understand what a vector is. Now you say you understand what is unit vector is. What is unit vector? Any vector whose magnitude is 1 is called as a unit vector. Okay.
Hmm.
Nothing is done. Okay, now you have to understand what is unit vector. Unit vector is a vector whose magnitude is equal to 1 and a specific direction. Okay, unit vector whose magnitude is 1. Magnitude of this vector is 1, right? Because how do we calculate the magnitude? X2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So if it is two-dimensional, it would be x2 minus x1 plus y2 minus y1 whole square. If it is three-dimensional, it becomes x2 minus x1, y2 minus y1 plus z2 minus z1. As and when the dimensions increases, the formula remains the same, but the dimensions will get added. Got it? So here we have three dimensions. So it becomes x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Okay, so that is how the magnitude of this vector is calculated. Now you have 3 points, you have three dimensions, so the third dimension got added. So if you have a fourth dimension, that will also get added. So it can be a2 minus i1 whole square. It's the same. So look at this I cap, j cap, and k cap. These are the standard notations for unit vectors along x-axis, unit vector along y-axis, and unit vector along z-axis. So I cap is the unit vector along x-axis, j cap is the unit vector along y-axis, k cap is the unit vector along z-axis. So that those are the standard notations that we do have in place. So if you call this as x-axis, y-axis, and z-axis, the unit vector along x-axis is called as I cap. Unit vector along y-axis is called as j cap.
Right.
Unit vector along k-axis is k cap. Z-axis is k cap. So vector, it has the direction. Direction has to match with the x-axis direction. This is x-axis. Unit vector along that direction should match, and it has a magnitude of length. What is magnitude? Magnitude is the length of the vector. Is called as the magnitude. Similarly, the vector along z-axis should have the vector along z-axis. Y-axis is called as j cap,
Yes.
and vector along z-axis, unit vector, whose magnitude is 1, is called as k cap. So that is called as unit. That is called actually unit vector means. Orthogonal vectors. What is orthogonal vectors are? Orthogonal vectors are vectors perpendicular to each other, right? So x-axis is perpendicular to y-axis. Look at your floor and look at the borders of your floor, the edges. They both meet at one place, right? They're going to meet like this. On the floor, they're going to meet like this, right? So they're going to meet like this. So what does this actually mean? So this is y-axis and this is x-axis. They are orthogonal to each other. I mean, the angle between them is 90 degrees. When the angle between two vectors is 90 degrees, we call them as orthogonal vectors. Okay. So look at this vector 1, 0, 0, 1. What is this vector means? What is 1, 0? Represent that on a 2D. So let's call this
X,
as
Y.
x-axis.
One is 0 is Y.
So 1, 0 is this, right?
Yes.
This is 1, 0. And what is 0, 1? This is 0, 1, right?
0, 1.
So you have a vector in this direction, you have a vector in this direction. So they both are perpendicular to each other, right? So the angle of
Yes.
them is 90 degrees. So that is the reason these two vectors are called as unit vectors, orthogonal vectors. And these
Vectors.
are unit vectors along x-axis and y-axis. 1, 0. So the unit is 1 here. The length of the vector is 1. And the length of the vector along y-axis is 1.
Yes.
The angle between them is 90 degrees. It's clearly visible. And, they are called as orthogonal vectors. And how do we, by just visualizing this, you are saying the angle between them is 90 degrees, right? It's easily understandable. But how to calculate this angle will also be learned later. So here is the formula right away. This is how you calculate the angle between two vectors. Okay, I'll also explain you that. But what is the dot product of two vectors? Dot product of two vectors is nothing but, let's suppose I have a vector like this, I have a vector like this. Dot product is nothing but just multiplying the numericals at the same places. So this is, can you say how many into how many dimensions this vector extended to or spread
N
to?
numbers. N numbers.
N dimensions, right? Because you
Yeah.
have n numericals in this vector. So this spread it into 2 dimensions because you have 2 points. This is a vector in n dimension. This is a vector in n dimension.
N numbers.
So yeah, you also have to understand the dot product of any two vectors is any two orthogonal vectors is 0. Before going there, you have to understand what is the dot product. Dot product is nothing but, this is called as the dot product between two vectors, and the formula is modulus of A, means the magnitude of A, and you also know how to calculate the magnitude of a vector, and this is vector B, and you also know how to calculate the magnitude of this vector, and cos theta, what is the angle between those two vectors. Theta is the angle between two vectors, and you have to apply cosine for that angle, and that becomes the dot product of two vectors. Mod A, mod B, and cos theta becomes the dot product of two vectors. Now let's take two vectors. As you know, what is I cap and what is j cap? What is
X
I cap?
vector, I cap.
Unit vector.
I cap is
Vector and X vector.
unit vector along x-axis, right? J cap is unit vector along
Y
Axis.
axis.
Y axis.
Okay, so now you want to try, you want to find out the dot product between two vectors I comma j. So those are your two vectors. Those are unit vectors along your x-axis. Unit vector j is unit vector along y-axis. So this can be represented as 1 comma 0, right? Unit vector along
Yes.
x-axis. If it is two-dimensional space.
0 1.
If it is, this is 0 1. If it is three-dimensional
0 1.
space, how do you represent I comma j comma k? If it is
Yes.
three-dimensional space. If this is three-dimensional space, these are the representations of I comma j in two-dimensional space. How do you represent the same in three-dimensional space? I comma j comma k.
1 comma 0 comma 0 0 comma 0 comma 1 comma 0
0
0
0
comma
0 1.
0 comma 1.
0, 1.
Okay, so this is the representation of vectors in the three-dimensional space, unit vectors in the three-dimensional space. Now you're trying to find out the dot product of two vectors. Okay, the dot product of two vectors in three-dimensional space is I comma j is the are the unit vectors along x and y axis. Now you're trying to find out the dot product between these two vectors. So dot product is nothing but, you know this point as 1 comma 0 comma 0, and you know this point as 0 comma 1 comma 0. uh, what is the dot product formula? Mod A mod B cos theta. Mod A means the magnitude of this vector. Magnitude of this vector is nothing but 1 minus 0 whole square plus 0 minus 0 whole square plus 0 minus 0 whole square to the square root. Right? You have seen the formula already. This is the formula for finding the magnitude of the vector x2 minus x1 whole square plus y2 minus y1 whole square. You remember that?
Yes.
Root plus
So what would be the magnitude of this vector now? 1 comma 0 comma 0.
1.
Root 2.
1, right? Because 1 minus 0 whole square would be
No
1.
minus 7.
0 minus 0 whole square is
0.
0. 0
0.
minus 0 whole square is 0. So root
0.
of 1 square would be 1. So the magnitude of this vector is also 1.
1.
1.
So you know A is 1, modulus of A is 1, modulus of A is 2, and cos of, what is that? Angle between I comma j. They are unit vectors along x and y axis. What is the angle between them? 90 degrees,
90
right?
degrees.
So cos 90. What is the value of cos 90?
0.
1 1 0. So the dot product of two unit vectors is 0.
0.
Okay, so the any two vectors I comma j would be 0, j comma k would be 0, because they both are orthogonal, right? X and y axis are orthogonal. This is how x and y looks like. So this is top, this is y axis, so they are orthogonal. X and Y are also, this is the bottom plane. So the angle between them is 90. If the X is extended to the top, angle is 90. So angle between X and Z is 90, Y and Z is 90, and also X and Y is 90. So dot product of any two vectors in any dimensions is 0. Okay, that is what it is. So now to simply to calculate, so how do you represent this vector? What is the vector representation? This is point representation, right? What is the vector representation of this? Did I told that? So this is the vector representation of 3 comma 4. What is the vector representation of this? This is 3 I cap plus 4 j cap.
4j, sir.
Because I is the unit vector along x-axis, j is unit
Yes.
vector along y-axis. So
Y-axis.
this point can be represented as 3i plus 4j. So that is the vector notation of any vector. So if I represent this a1, a2, a3 in vector form, how do you represent that? a1 I cap plus a2 j cap plus a3, right?
Okay.
So we have understood about like I dot j. So now you have seen I dot j is equal to 0, right? That's what you have seen right now. So you have understood that I dot j is equal to 0. Agreed?
Yes.
Now
Yes.
now tell me what is I dot I?
1.
One.
Perfect. So I dot I, what is angle between I and I? Vector I and vector I.
0.
0.
0.
Yeah. The reason being they both lie on the same place. They both
Same.
directly same axis. So I is a unit vector on x-axis and I is also unit vector on x-axis. So they both are parallel vectors. So the angle between them is 0. So cos 0 would become 1. 1 dot 1 into 1 into 1 will become 1. Now if I have to represent this in vectorial form, I1 A1 I cap plus A2 J cap plus A3 K cap plus so on so on so on AN some numerical cap, right? Dot product of this with, we are doing with B1 I cap plus B2 J cap plus so on Bn N cap.
And
You know, I dot I will be 1, I dot J will be 0. So I dot any other unit vector will be 0 in any other direction. It can be n directions. Let's suppose x is perpendicular to Z is perpendicular to Y, Z is perpendicular to X, Y is perpendicular to Y, right? Only dot product of unit vectors in the same direction will be 1. Perpendicular, rest of all unit vectors will be orthogonal in any direction. So, so we when you multiply them, they become a1 dot b1. So rest all will become a1 I dot b2 j will become 0. a1 I dot b2 n will become 0. So we'll have only a1 b1. So we'll have a2 b2, a3 b3. So the dot product of any two vectors will become a1 b1, a2 b2, so on, something of that.
A and B.
Right? Understood that?
Yes.
Right. Now you have to understand the other formula for the dot product. A dot B is equal to A bar, I mean modulus of A, modulus of B and cos theta. So you have to find the angle between two vectors. I was given two vectors A comma B. If I have to find out the angle between two vectors, I have to apply this formula. The formula is, you can calculate the dot product of two vectors and also you can calculate the modulus of two vectors. So cos inverse of this would become the angle between two vectors. So if you take an example, let's take the example, the same example. So 1 comma 0 and 0 comma 1. So cos theta would become, what would cos theta would become? So 1 dot 0,
6.
this can be represented as I, right? The other one will be represented as J. So I dot J will become I dot J,
0.
I dot J.
0.
So I dot j becomes 0. Magnitude of I is 1, magnitude of j is 1. So cos
1.
theta is equal to 0. Then theta becomes what? When cos theta is equal to 0. When theta is equal to 90 degrees, cos theta will be
Cos
0. So the angle between
Cross
I and
90.
J is 90 degrees, which we already know.
yes.
Understood? That is how you calculate the angle between two vectors. Okay.
Yes.
Yeah. So all these concepts will be useful. I know many of you might be aware of these simple things, but I'm just revising this because we will get in touch with all of these at every point when we analyze the complex stuff which we are going to learn. Um, we almost moved to statistics, but I just want to. I don't know if I have that slide ready with me, but we will use these vector notations at many points. Where is that? I have that slide somewhere, but I just want to show you how do we use vectors. We have like principal component analysis. I think I have my slide somewhere else, but there, this vector notation is very important. We use these formulas only to derive a complex stuff. So you understand this slide, right? Can we go to the next one?
Yes.
Yeah. So starting here, we move to statistics. We understood what the matrix is. We've understood the basics of vectors, and now we are going to move to statistics, and which is very important to understand. So statistics is again a study of it's the study of collecting, analyzing the data, interpretation of the data, and presentation of the data. What we do is in any stuff that we do, any data stuff that we do, what we do, the first thing is we collect the data from different sources. It can be from different servers, it can be from databases or whatever it is. We collect the data and then we analyze the data. As I shown you earlier, we pre-process the data, we analyze the data, we interpret the data, we try to understand the data, and then we present the data. So that is what all statistics basically do. So in statistics, what is more important is to understand what is the central tendency of the data. To understand what is central tendency, you can easily say this. Let's suppose you can take an example of um, India. So you can take the population of India. So when you look at the population of India, what can be told? So you can say the young population is in India is very more, right? So you are looking at the population and you're saying that the young population is in India is very high. The reason why you're able to say that is, by looking at most of the stuff around you, right? So that is what central tendency means. If you want to keep the example little easier, if you are in a class and if you look at the average marks that I mean, what is the average of marks? What is the most common marks that are obtained by the students? Can be somewhere in middle, right? Not everyone will get 100 percentage, not everyone will fail the subjects. So but most of the students will be at somewhere around 80 to 90 marks, right? So that is what central tendency means. Central tendency means where the most of the data points lie is what central tendency is. Even if you take the heights of the students in a class, so not everyone will be so tall beyond 6 feet, or not everyone will be very short, like 3 feet or something. You rarely see those cases. Beyond 6 feet, less than 3 feet, you rarely see those cases. But most of the students will be somewhere around 5 feet, 5.5 feet. You can say the central tendency of the data of the students is the data here. So the central tendency lies around 5 feet and 5.5 feet. So that is what central tendency means. Understood? So you can take many examples of this, but using that data, you can say what is the central tendency of this village. Take a particular village. If you look at that village surroundings, you can say whether the people are rich or not in that village by looking at the houses, the work that the people are doing, the business that is carried out in that particular village. By looking at all this stuff, you can say the richness of the people living in that village, right? That is what central tendency means. You look at every data, you look at tall people, you look at short people, but you say most of the students in this class are lying in between 5 and 5.6 feet. It doesn't mean that you're not taking those endpoints or those outliers. Okay, you're considering those heights as well, but you come into a prediction that students in this class are on an average around 5.5 feet. That's what you say. That describes the data. That describes the height of the students in that particular class. That is what central tendency means. Central tendency is basically a single value that describes the population, that describes the whole student's height. Okay, that is what central tendency means. Now, how to calculate that central tendency when different data points are given? So what are data points? Data points are nothing but the heights of students in the class, right? Those are the data points in this class. Now, if you want to find out the central tendency of those data points, you have different methods to do that. Central tendency is basically calculated using mean, median, and mode. And how do we calculate ththose values? I'll shortly show you the formulas, but I just want to make sure you understood what central tendency is and how the central tendency plays a major role in describing the data. Okay. Are you clear with what central tendency is?
Yes.
Okay. So now one of the central tendency calculation is mean. So you can use all these three methods, mean, mode, and median. You can all use all of this, but when to use what is what is important to understand. It's like these are just formulas, and it is easy to understand as well, and it is easy to calculate. But you have to understand when to use what. By looking at the data, you will understand. You should understand like what central tendency method to be used to describe that data is something which you have to understand. Now let's given it's given that I now I'm going to take an example here. Okay, what that example says is that I do have an example over here as well. I can just represent the data points over here. So now let's understand how to calculate the mean of given data points. Mean is nothing but the average of the data. Average is nothing but sum of the data points by number of data points. Okay, sum of the values of the data points by number of values. Is that clear? It's an average. Mean is just the average of the data points. If I'm given with, I have 3 feet by one of the students, is the height of one of students 5. I have 5.5, I have 5.6, I have 5.7, and I have 6.5. If I have to calculate the mean of this, how do you calculate that?
3
Calculate.
plus
Hmm.
Sum
3
of
plus
all values
Yeah,
by or 6.
by
6.
6.5.
Yeah, 3 plus 5 plus 5.5 plus
6
5.6 plus
6.6 plus
5.7 plus
5.7 plus
6.5
6.5.
by
by 6. By 6.
6.5.
6, right? So the total data points here is 6, and the sum of data points is, and we are going to calculate sum of data points by number of data points. So what
Number.
is the sum here? 3 plus 5 plus 5.5 plus 5.6 plus 6.5.
32.5. 32.1.
32.1.
1 by
That
6.
31.3, right?
Oh, yes.
uh,
31.3.
31.3 divided by 6. What is the value?
5 point.
that
5.21. So where does 5.21 falls? 5.21 falls somewhere in between this. So look at this. This is somewhere between the data where most of the data points are residing, right? So that is the reason why we say mean can detect the central tendency of the data. It can describe most of the data points, right? So it is not somewhere around 6. The mean is not coming as 6, or the mean is not coming as 4, where there are less data points. The mean is residing in between the points where most of the data points are residing. That is why mean is called a central tendency measuring parameter. Understood that? Okay. So now that mean is one of the central tendency measuring ways. The other one is median. Median also measures the central tendency. How do we measure the mean is arrange the numbers in ascending order or descending order and take the middlemost value out of those values, and that will become the median of the data. So if you consider the same example, the same data, what is the data? The data is 3, 5,
5.5,
5.5,
5.5,
5.5,
5.6,
5.6, 5.7,
5.7, 6.5.
and 6.5. So I arranged the data in the ascending order, right? And now I have to take the middlemost value inside this. So what is the middle value in this data? I have 6 numbers here. What is the middle data? What is the middlemost data? You're not
2
able to see
numbers
that,
is
right? Because you have 2 numbers. Let's suppose I'm adding in another height, which is 6 feet. Let me add 6 point, what to say? I'll add 6.6. So as we already arranged them in ascending order, let me add another point, which is 6.6. Now tell me, what is the middle value of this data? What is the median of this data?
5.6, 5.6.
5.6, because you have 3 members on the left side, you have 3 members on the right side, so 5.6 will become the middlemost, right? So that describes the whole data. That is what median basically means is. Okay. Now let's exclude 6.5 again. If there are 7, you are finding out the middle one. You're able to find, if you have odd numbers, you're able to find the middle element inside that. If you don't have the odd ones, if you have even numbers, even number of data points, how are you going to find out the median? Something which you're going to do that now. Okay. That is what you will try to understand now. Okay. So now I have 6 elements. If look at this, so middle value of the given data set when arranged in a particular direction um, is called as
Mean.
median. If the number of values or observations in the given data is odd, then the median is given by n plus 1th observation. So in our case, 7, when we have 7 values, 7 plus 1, which is 8, 8 by 2 is 4. So the fourth element, which is 5.6, is the median. You can easily find that when they are odd. If they are even, the median is given by n by 2 and n by 2 plus 1th observation. Average is nothing but sum of numbers by number of elements. So you have even 6 by 2 is 3. So third element and 3 plus 1,
Fourth element.
fourth element. You have to
Fourth
take the
element.
average of 2 elements, which will give you the what is that? Which will give you the um,
Median.
median of the number. So 5.5 by 5.5 plus 5.6 by 2 would be the median. 5.5 plus 5.6 by 2.
11.1 by 2.
So it will be 11.1 by 2, somewhere around 5.5,
5
right?
point.
5.
7.1 divided by 2, which would be 5.55. So this is also effectively giving the median value of these data points. So the mean is giving 5.21 and median is giving 5.5,
5.5.
right? What do you think is giving the better central tendency, mean or median?
Median.
median is giving better central tendency, right? Because these are the data points, most of the data points residing, and median is staying here, and mean is staying here. This is the mean, and this is the median. Median is exactly sitting middle at the center of most of the data points, which commonly better which is commonly describing the data in a much better way. But this is residing at most of the data points, but it is slightly left. Okay, now you understand how to calculate the mean and median, and you also have understood what is central tendency is. Now you have to carefully understand when to use mean and when to use median, and you also will understand what an outlier basically means. What are called as outliers. Some data points are called as outliers. Remember this word outlier. Can you say something by listening to this word outlier?
Mohan.
Yeah. So outliers are basically which is deviating the data points. So look at this. Let's suppose I have a context. I have a competition where the competition is to run 5 kilometers, and I recorded, you know, so the better example would be, let's suppose I recorded the ages of different participants who completed the 5 kilometers in 20 minutes. Okay. So when I recorded this data, uh, I collected 100 persons data. So I collected like data of 100 people who ran, um, the 5 kilometers in 20 minutes. So when I see the age of all the 100 data points, so most of the people are in between 20 and 25 age. Okay. So most of the people who completed that 5 kilometers in 20 minutes, age is in between 20 and 25, 20 age is between 20 to 25 years. But I have three persons whose age is 85, 90 and 100 years. Those three people also completed 5 kilometers in, you know, 20 minutes. But their age is deviating, is completely deviating most of the data points, or most of the people who completed that particular run in that particular time. So you call these as outliers. The reason being, if you consider these people out of 197 are in between 20 to 25, and three people are of age 80, 90 and 100. If you consider these data points for your analysis, it will give you completely wrong results. Okay, such data points are called as outliers. I mean, outliers are, in short, that happened in real, and we cannot completely assure, but that is out of, beyond the possibility. It happened, but that is happened beyond possibility because of different reasons. He might be having very good health maintenance, very balanced diet maintenance over all these years. That's the reason he had lots of practice all these years. His mental strength is very good. That's why he was able to, those people were able to do it. But practically, it is impossible. But if you're trying to analyze, if you are trying to extract some information out of the data, so you might have provided that computation. You have provided. You have conducted that context within 1,000 people, but only 100 people achieved that. But you want to understand what are the factors that helped those people to achieve that task in that particular amount of time, so that you can extract that information and implement that on other students as well, or who is trying to do that. If you use that information, provide some better diet plans, some better quality of like training can be provided, that information can be extracted out of these data points, which is 97 people. But if you include these three old persons as well, your information would be definitely wrong, because those are outliers. They will impact your analysis. So for that, those are called as outliers. But for that to be shown on in numbers, I have taken this example. Look at this. By looking at this, can you point out what is an outlier here? So you have these ages 1, 2, 3, 4, 5, and 100. Can you figure out what is an outlier here?
100.
Why?
Because up to 1 to 8, there are very closer.
Right. So we have most of the points lying at some area, but there is one point which is lying far from these points, from most of the data points. So what happens if you include this outlier into your analysis? Okay. So if you want to describe this data with one point, what you will calculate? So you have n number of data points and you want to describe the data, what you will go with? Is that central tendency? Hello?
Can you repeat the question again?
So now I have this data, right? I have these data points represented in 1D. I have taken this dimension, which is A's, and I'm representing the A's in one dimension. And this is how I represent it. Now, if I want to describe this data, so if I want to describe this data, what are the statistical parameters that I have to, say to describe this data with a single point? In the previous slide, you have studied about central tendency, right? What central tendency is? It describes the entire collection, right? We tend to represent a set of data by representative value, which would approximately define the entire collection. Collection is nothing but set of data points. So similarly, for all these data points, if you want to represent that with a single value, if you want to describe this data set with a single value, how can you actually describe that? If you calculate the mean of this, will that represent this data set? If you calculate the median of this, will that represent this data set?
Median of the data set.
Yeah, both mean and median both describes the central tendency, both describes the data with a single value, right? If you take the heights of the students in a class, when you calculated the median, it says, so you can simply say the average, most of the students in this class are, uh, most of the
Okay.
students height in this class is 5.5 feet or 5.1 feet. When you calculate mean, you said it is 5.1 feet. When you calculate median, you said it is 5.5 feet. Now, calculate the mean of this data. Then you will understand. I mean, now the only question is when to use mean and when to use median. Both are the central tendency representations. Both are the single value representation of the data set. But when to use what is the question right now for you. So to answer that, you should be able to calculate the mean and median of this data set. What is the mean of this data set? What is
Sum
the
of the all. Sum of all.
sum of numbers by Number of
Number of
points in this data.
number of data set.
So what mean becomes now? What is mean?
It's
Mean
average.
5.
Yeah. So it is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 100. Right? By how
By
many
9.
data
100.
points? 3
Okay.
by
Okay.
9,
9.
right?
By 9.
9. Okay.
Number of points in the data set. We have
Okay.
9
Okay.
data points. So the sum of numbers by number of numbers. So what is the mean here now? If you calculate the mean, what is the value it is coming now?
15.
So if you use your calculator and say me that answer, uh, I'll just place it over here. And we have median as well.
136.
136.
136 by 9.
What is the value? It's been
15.11. 136.
50.11. So mean is
Yes.
value, right? So this is mean.
Yeah.
Okay. And now what is the median?
5.
5 is the median.
5 is the median, right? So this is median and this is mean. Now what do you think? Mean is 15.11 and median is 5. So what do you think better represented the data, mean or median?
Median.
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 Median, right? Median is the better representation of the data because it actually residing exactly at the center of most of the data points, right?
Yes.
Understood. Now, but mean is residing outside. It's residing little closer to most of the data points, but outside of the outside, it's behind. I mean, it's staying far from the most of the data points, right? Where most of the from the area where most of the data points are residing, it is staying far from that point. But median is residing in between most of the data points. So in this case, median is the better central tendency parameter. So with this in place, you can say this, you will understand this. Mean works well when the data is symmetrically distributed and free of outliers. When the data is evenly distributed and when you don't have outliers, you will go with the mean. Okay. Median is ideal for data with outliers. When you have outliers, median is the ideal one. Understood? When to use and when to use mean and when to use median. Median should be used as a central tendency statistical parameter when you have outliers in your data. When you don't have outliers in your data and your data is symmetric, you need to go with calculating the mean value to represent the whole data set with a single value. Is that clear?
Yes.
Okay. Now you have to understand what a mode is. Mode means most frequently occurring, uh, it can be most frequent occurring value in the data. It doesn't necessarily need to be a number. It can be anything. It doesn't needs to be only numerical values. It can be a categorical variable or whatever it is. But most frequently occurring data or value in the data is called as mode. So no mode when all are unique. When all the values in the data are unique, the mode will be zero. We say there is no mode for the data. So if you look at this data, what is the mode of this data?
0.
Zero, because everything is unique. Now, if you look at this data, what is the data? Can you calculate mean for this data?
Yeah. 15.11.
The data below. Can you calculate the mean or median for this data?
Okay.
Categorical data.
No.
Mean.
You cannot calculate mean or median for this data because they are not
Yes.
numericals. Mean and
Not an.
mean and median can be calculated only when the data is numerical. But for categorical variables, you can calculate the mode. So mode is the central tendency representation for the categorical data. So is this category, if this is categorical data, what kind of categorical data is this? Is this nominal or ordinal?
Nominal.
Why?
Nominal.
Why is this nominal?
These are the inputs.
Because
This
those are not in a order.
Yes,
order.
there is no defined order in the data. That's the reason these are nominal categorical variables. So when you have categorical data, the central tendency measure is mode. Mode is nothing but most frequently or more frequently occurring value in the data. So in this data, the most frequently occurred is data, right? So that is the reason the mode of this data is data. So you have data occurring 6 times, ML occurring 2 times, A occurring 3 times, RAG occurring 2 times, LLM occurring 2 times. So data occurred most of the time. So data is the central tendency of this categorical data. So mode also always has to be used with the categorical data. Okay, you cannot use mean or median, but when you have outliers, go with median. When you don't have outliers and you have data symmetrical, you have to go with mean. But for most of the uh, you know uh, machine learning stuff, we always calculate mean. We always consider mean as a central tendency parameter. Okay, it depends on the data as well, and the way you go with your model building. But mean is the most frequently used when compared to median. But when you have outliers and you haven't get rid of outliers in your data, it's better to go with median. Okay, so what you have learned right now is what is central tendency, how to calculate mean, how to calculate median, how to calculate mode, when to use median and when to use mode, what is an outlier in the data, and you also have learned about using mode for categorical data. That's what you have learned in the last 2 slides. Clear?
Yes.
Yes.
Okay, so going back to the next slide, variance. So this is very, very important stuff. So keep focusing on this. Variance says mean. What does mean says? Mean represents the central point of the data, right? It's a single value that represents the data, right? So if I draw a diagram for you, mm, I'll just draw a diagram or some set of points in 2D space, and that will give you a good understanding. So I have a data in my two-dimensional space. When I say two-dimensional space, this is X and this is Y. I have my data points here. I have my data points somewhere like here. So you can take any of the examples, doesn't necessarily needs to be X and Y axis. You can take this as height of the students, and you can take this as uh, you know
Number of students.
amount of food that student consumes, amount of food student consumes. It can be 100 grams, 200 grams, 300 grams, 400 grams, 500 grams, or something like this. This is in feet: 5 feet, 6 feet, 7 feet, 8 feet, something like that. So one student ate 200 grams and his height is this. Other student ate 700 grams and his height is 6 feet. So that is what these data points actually means. Okay. So that is how you have to understand the data points. Now you have seen the data points. Where do you think the mean lies for these data points? So the mean lies somewhere here, right? In the middle of the data set. Is that right? So mean is the central tendency, agreed? Mean represents the average of all the data, the average by total number of values. Basically, it represents the middlemost value inside the data points. That's what you have seen here in the previous screen. You have calculated the median, which is 5, and you have calculated the mean, which is around 11. It is always trying to represent the center of all the data points, right? This is where most of the data points writes, and the mean is trying to represent the center of the data set. That is what mean median will do, right? So if you go back to the next slide, so these are the data points that I do have. If I calculate the mean of these data points, it resides somewhere here, right? Because that is the center of all the data points. Is that clear, or any questions here? Hello?
It's clear.
Here.
Now, if you have to understand the variance basically specifies what is the spread of the data points from the mean, how far the data points are dispersed. So this length will be given by the variance. Variance specifies from the mean how far the data points spread. Okay, that is what the variance actually gives. So the variance can be low. What happens if the variance is low? I said the dispersion of the points from the mean is what variance says. What does means if the variance is low? If the variance is low, all the data points will lie around the mean. Okay, so if the variance is low, all the data points will lie surrounding the mean. Okay, so this is how I can draw it. So okay, this is how I can draw it. So if the variance is low, most of the data points will only lie here. So we won't have these data points. If the variance is little high, they will spread like this. If it is little more high, they spread like this. As the variance increases, the data points spread from the mean will also increase. If the variance decreases, they come more closer to the mean. Most of all the data points will lie surrounding the mean. That is what low variance means. If the variance is increasing, the points will move more farther from the mean. They will go more away from the spread, more away from the mean. That is what more variance means. Variance just measures the dispersion of the data points from the mean. Okay. Look at this. Variance is a statistical measure that indicates how much the values of the data set differ from the mean or differ from the mean of the data. It reflects the spread or dispersion of the data points. Got it? So now to calculate that variance, to know how far the points dispersed from the mean, you have this formula, which is 1 by n. This is the summation. This is called a summation of the data from I is equal to 1 to n, xi minus mu whole square. Mu is the mean over here. Mu is the mean of the data set. Sigma square is the variance of the data set. Xi is each individual data point. N is the number of data points. Now let's calculate the variance of this data set. Can someone say how to calculate the variance of this data set? So the first step is to calculate the mean of this data set. What is the mean of this data set? Hello?
$19.1 is the mean.
19.1.
Yes, Anya.
So now can we calculate the variance by using the above formula? How to apply the above formula?
1 by n is nothing but
19.
number of data points. That is 1, 2, 3, 4, 5, 6 number of
6.
points. 1 sigma I is equals to 1 to 6.
Hmm.
Xi value each individual point.
Hmm.
Okay, 1 minus 9.1 whole square.
Awesome. Next. So 1 by 6 and
6 sigma
1 minus
1 minus 9.
9.16 whole square. Okay, what's
Yes. What's the answer?
no, there is still, look at this. This is called a summation from I is equal to 1 to n, means I has to be 1, I has to be 2, I has to be 3. It goes until number of points. In our example, we have total 6 points. So n will be 6 now. So I runs from 1 to 6. It goes from x1 minus mu whole square plus x2 minus mu whole square plus x3 minus mu whole square plus go on x6 minus mu whole square. So now you applied x1, which is 1, and the x2 will become 2 minus 19.6 whole square
Whole square.
plus 3 minus 19.6 whole square plus 4 minus 19.6 whole square, 5 minus 19.616 whole square, plus 100 minus
100
19.6
minus
whole square.
90.
So you, if you calculate that, you will get the variance. And if now you got the mean as 19.16, and if you calculate the variance, then you will come to know what is exactly the variance means for this data by just converting that into geometrical view. I just have given the timeline, I mean, the point line over here as well. We can draw the points there, and also you can see how that looks like, how the variance looks like, and how the means look like on the data. Just calculate the variance of the data using this formula, and let me know, and then we can go from there. Yes, what is the actual interpretation of that variance? But look at here. So I used this copilot to calculate the mean variance and the mean variance. So 19.17 and the variance is 1308.47, right? So variance is given as 1308.47, which is too high. I'll let you know why the value is too high, and why variance, how variance indicates the spread of the data points, and why it is too high. So I'm representing these points. One stays here, right? So this is one of the point. 2 is another point. 3 is another point. 4 is another point. 5 is another point, and 100 is another point. So these are my data points. And now where my mean is now. Now, where is my mean? Mean is 19.16, right? 19.16 stays somewhere around here. Mean lies somewhere around here. 19.16 means it will lie somewhere over here, right? So this is 19.16, this is 19.16. So now I said variance is 13,008.47, right? Which is too high. That means it says from the mean, the points spread 1300 units on both the sides. But the actual spread of the data points from this is 19.17. So the points are still 1. It means like the actual spread is just this one, right? The actual spread is this from up to 100. So 19.16 to 100 is somewhere around 80.9, right? And the spread of data points from 19.6 to 1 is 18. So the ideal value is the maximum value for the variance, the best value for the variance is 18.9, right? Because it specifies the values 89, if it is somewhere around 18, it's a good coverage, because most of the data points are this side, and the variance of the data points, I mean the spread of data points from the mean, is described by this value 18. This is good. Or 89.9. If it is coming as 80.9, then it says like 80.9 units spread this side, and 80.9 units got spread this side. So this is a good measure, but variance is giving us 1300, which is way beyond 80.9, because this is the mean. These are the data points. So the data points spread from the mean, how far they are from the mean, how far they spread from the mean. The maximum is 80.9, because 100 is far away from the mean, which is 80.9 units from the mean. And here it is just 18 units spread from the mean. So if it is somewhere around between 18 and 18.9, that is a good deal. That's a good description of the variance. But right now the variance is giving it as 13,000. It means this value of variance is saying that from the mean, the spread of points is 1300 units from the mean, which is not at all real. So you can conclude that this is not a good deal. A higher variance means the data points are spread out widely from the mean, while lower variance means the data points are closer to the mean. That's what I'm trying to explain here. When the variance is high, they spread far away from the mean. When the variance is low, the points lies closer to the mean. The spread will be low from the mean. Understood? But here in this case, it gave the variance as 1308, which is not at all acceptable, because we just have the point spread maximum of 80.9 units or 81 units. The reason why the variance is giving this value is, and variance is not a good measure and we will never use variance. That's the second thing. But why variance is giving that high values? The reason is it is squaring the points, right? It is doing a square. Let's suppose the units of this is height. Let's suppose the units of this measurement is called as feet. I'll take these as heights of the students, 1 2 3 4 5 as a height of the students, and the units of this is feet. And what is variance is doing? It is doing a square of the unit. That means it is doing feet square. It is completely changing the units of the measurement. So the scale of this units is becoming square. That is the reason it is not giving the right variance value. Okay, let's suppose if you square this, if you square 1300, what is the value of this? It would be somewhere around 13.8. Means what is the value of it? It would be somewhere around 36. Is that right? No. What is the square root of 1308? 36.17. Okay. So this is when you bring the variance back to the same units. So this is square, right? This is squaring all the values. If I apply square root to this, what happens? It again becomes the feet. The same units as the same units as the data. So when you do a square root of this value, it is coming as 36.17. That means the spread of the data from the mean is 36.17, which is a good deal, because the spread is the most of the points lies within 18 units, and the outlier is lying 80.9 units. So 36.17 is a good measure of the variance. I mean, of the spread of or the dispersion of the points from the mean. Clear? Why the variance is
Yes.
giving a high value? Why do we need to do a square root for that? Because you are changing the units of the data. You're doing a square of the data. So the scale will become square. So you have to, if you want to bring back that to the normal units back again, you have to do a square root. So the square root is giving a good value. The 36.17 is a good spread or good dispersion measurement. So when you do a square root for that, we call that as standard deviation. Okay, so this is variance. When you do a square root for this variance, we call that as standard deviation. So you have done a square root for this. and that is called as standard deviation. So this is the standard deviation formula. Standard deviation is the square root of the variance and measures the average spread of the data points relative to the mean. More intuition as it tells you how far the data points tends to deviate from the mean in the same units as the original data. This is what we were saying, right? Same units. We are bringing back the variance into the same units of the original data. If the data is in feet, the standard deviation will also be in the feet. So it's a good measurement. Okay. So in most of our data analysis stuff, we do standard deviation. We don't use variance. Variance is not the units of the variance is not the units of the original data. We are scaling that units of the original data, whereas standard deviation units will be the same units of the original data. So that is what standard deviation means. Understood? Is everyone
Yes.
active? Are we going beyond the timelines today? Do you want me to stop? So what I'll do is I'll just cover this next slide and I'll stop so we can again see the rest of the stuff tomorrow, which is very important related to probability. But I'll just we know what is standard deviation now. You also have to understand what is mean absolute deviation. Mean absolute deviation is another measure of dispersion of the data from the mean. The formula for this is simple. 1 by n sigma 1 equal to I to n xi minus mu. Okay. You know how to calculate the stand you use now you know what is the summation and how to calculate the values. So I'm giving a simple example for you. Tell me what is the standard mean absolute deviation for this. So if I'm giving this data, what is the mean absolute deviation for this data and how do you calculate that? Tell me the equation for calculating that mean
One, 1/6.
1 by
1
6.
by 6.
Hmm.
Sigma
Hmm.
I equal to 1.
Hmm.
1 minus 5, 6, 6, 10, 15. 21 by 6.
So you want me to calculate the mean? I can do that quickly. 1 plus 2 plus 3 plus 4 plus 5 plus 6
21 by 6.
divided by 6. So 3.5 is the mean. So how do you apply this now?
1 minus 3.5.
What's next?
Plus.
So understand this summation in a better way. So I'm writing it for you. So I equal to 1 to 6, n is 6 here. Xi is the value, right? Xi minus mu. Mu is 3.5. Now what is this summation means is 1 by 6. So this sigma is the sum. You have to sum the values. Now apply I to this xi. So xi minus 3, x1 minus 3.5. After 1, what do you have to get? X2 minus 3.5.
2 minus
Okay. I
3.5.
will get all the values from 1 to 6. That is what it means. And you have to sum the resultant expressions. I replace I with 1 to 6. I will get all the values from 1 to 6 and you have to sum the equation. So x1 minus 3.5, x2 minus 3.5 plus x3 minus 3.5 plus x4 minus 3.5 plus x5 minus 3.5 plus x6 minus 3.5. So I goes from 1 to 6. And then you have to add all that resultant data. Now that becomes 1 by 6 into 1 minus 3.5, 2 minus 3.5, 3 minus 3.5, 4 minus 3.5, 5 minus 3.5, 6 minus 3.5. So when you add all that data, it becomes mean absolute deviation. Well, but look at this double slashes, I mean double lines here, pipes. So that means absolute values. What is absolute value means is, let's suppose 1 minus 3.5 will be modulus of
Mean
Minus.
minus
value
3.5. So when you have this absolute, minus will also become
2.5
plus.
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 Okay, so minus will never be minus. When you say absolute, it becomes plus 2.5. Understood? So it becomes 1 by 6 into 2.5 plus 2 minus 3.5 would be 1.5. Basically, it is minus 1.5, but
You
as you are
mod
applying absolute, it becomes 1.5. Plus 3 minus 3.5 is 0.5. Plus 4 minus 3.5 will be 0.5. 5 minus 3.5 will be 1.5. And this will be 2.5.
5.
Right? So 2.5 plus 2.5, 5, 6, 9 by 6. So 9 by 6, which is 3 by 2, which is 1.5. So that is the mean absolute deviation for this data. So mean for this data is 3.5. So it is saying the spread is 1.5 from on both the sides. So this side 1.5 and this side 1.5. That is what it is saying. Okay. So now this is also a measure, like we understood when to use mean and when to use median based on outliers. Now you also have to understand when to use standard deviation and when to use mean absolute deviation as the variance to measure the dispersion of the data from the mean. So that is what our next slide says. So now we are calculating the data. Okay. You're calculating the standard deviation for this data. What you have done, 2, 4, 6, 8, 10 are the points. Mean for this points is this one. And square deviation. What is the calculation of standard deviation? X minus mu whole square by n square root of that value. So you're getting the square deviation by number of data points, which is 5. So I'll tell you why it is mentioned as 4 here. There is an Bessel's, we call that as Bessel's normalization, but I'll tell you later why we are applying 4 over here. But you can even do 5 as well, just the number of samples. So average of square deviations, which is 1600, and when you apply the square root of that, it becomes 40. Okay, so the standard deviation for this data is 40, and the mean absolute deviation for this data is 30.4. Okay, so standard deviation is 40, highly influenced by the outlier, less influenced by the outlier. You also know what is outlier. If you mark these points on a line, so 2, 4, 6, 8, and 100, you know 100 is an outlier, right? And now what is the mean? 24. And what this 40 says is that the from the mean, the point spread 40 units this side and 40 units this side. It is not actually 40 units. What is the actual dispersion from the mean? 24 minus 2, which is 22 units spread from the mean. As this is outlier, the maximum that it is happening here is that 76 is the maximum deviation on this side. But technically, anything beyond 22 is a good measure. Okay, so standard deviation is giving 40 units spread, but the actual is just 22. Whereas mean absolute deviation is giving, what is mean absolute deviation is giving? Mean absolute deviation is giving just 30 units spread. So this says from the mean, the data spread just 30 units. So, but the actual is just 22. Now, what is a good measure? This is mean absolute deviation and this is standard deviation. What is a good variance measure in this case?
Mean absolute deviation.
Yeah, why? The reason is it is little closer to
Uh,
the actual
30.
dispersion. The actual dispersion is
Well,
20, which is little closer. But standard deviation is beyond that dispersion. The actual is just 22, but it is saying the dispersion is 40, which is almost double to it. But mean absolute deviation is little closer to the actual deviation. So again, standard deviation has to be used when the data is normally distributed. Okay, remember this word, normally distributed. We have two different slides for this single word. Okay. So this is how the data, normally distributed data, looks like. I'll also give you just an example for your understanding, but this is how a normally distributed data looks like. Okay. I'll also tell you the intuition behind this graph, but and outliers are not a concern. So when outliers are not a concern, go with the standard deviation. Outliers are not a concern means your data might not have so many outliers. When you need a measure of variability that is less sensitive to outliers. So to keep it short, standard deviation has to be used when the data is normally distributed, and outliers is not a concern when your data don't have outliers, is what if you believe. But if your data is sensitive to outliers, if you have outliers in your data, go with mean absolute deviation to get the right amount of variance. Understood? That is what basically standard deviation and mean absolute deviation is. I don't start probability, but I'll just explain you what normal distribution is with an example. When they say data is normally distributed, you have to use standard deviation for the data which is normally distributed. When they say that, you have to understand what is normally distribution. What is data normally distributed basically means is what you have to understood. So I'll take this slide away. Okay. Now understand what is data normally distributed means. It's very, very important. So just get an intuition now, and then we have different slides placed for this concept all alone. Now I'll take an example. Okay. Again, I'm taking the example of students' height in a class. Okay. Let's take the sample of, this is 0, this is 6 feet. This is, let's suppose 5 feet. Let's take 20 students, and also let me know if you agree with this data or not. I think I'll just split this in this way. I have 3 students, 17 students. Sorry, this cannot be 17. 13 students, I would say. So I'll say 13 students, and I'll say another 3 students. So this combines to 20 students, right? So let's say these are tall students, these are short students, average height students. Okay, so let me divide this into bins. Okay, I'll say 5.2 to 5.7 is small, not 5.7, I would say 5.6. Do you think most of the students fall in this area? 13 students. That's how the heights of students in a class will be. Most of the students will be in between the will be in that range, right? Average height, right? Right? Agreed? Or do you think it would be different? Hello? Yeah. So just understand this. Let's suppose I'm further breaking down these into students. So these 13 students I'm breaking down to different ways. So in this, I would say 5.5 would be 6 members, and 5.6 would be somewhere around 4 members, and 5.2 would be somewhere around 3 members. Okay, so that's how basically around the mean of the data, more data points will be there. That's the whole concept. That is what central tendency means. Central tendency, basically what it measures the center point. Center point means where most of the data points reside is what central tendency basically measures. So if you say mean of the heights of a class is 5.5, most of the students will reside around that point. So if you calculate the number of students, so number of students at this point is, what is this point? We say mean 5.5, we have 6 students here. Okay, at 5.6 we have 4 students. I mean somewhere around, so this is 6 and so this is 4 students here. Okay, at 5.2 we have 3 students. So at 5.2 we have 3 students, and somewhere short students are around 3 and long students are around 3. Okay, this is how the graph is. Now if you draw this graph, how does that looks like? If you draw a graph above that line, just look at how that looks like. So I'm just joining the endpoints of all of this. So look at this. How is that looking like? Is that looking like this? So such kind of data is called as normally distributed data. Normally distributed data means most of the data points are residing around the mean, and as they move farther from the mean, the data points will become less. That is what normally distribution means. So at this point, look at this. At this point, you have, this is the mean, 0 is the mean. So most of the data points are surrounding the mean. When we go far from the mean, the data points are becoming 0. So this is what it is represented here as well. If I remove all of this stuff, I'll remove all of this stuff. Uh, Point option. Look at this. So what this actually says is 68.26 percentage of data or data points are 1 unit away from mean. So this is mean. So they are just 1 unit away from the mean. So we call this as standard deviation. How far the points spread. This is called as one standard deviation. Actually, the spread of the data points from the mean. This is the mean and this is one standard deviation. So in one standard deviation, we have around 68.26 percentage of data points. Okay, within two standard deviations, we have 95.44 percentage of points. What you just have to understand is most of the data points will be around the mean. As we go far away from the mean, the number of data points will actually get reduced. Okay, so this height is the measure of number of data points in that particular bin. So if this is 5.2 to 5.3 height persons data, this bin is that data. So the number of students in that bin would be this height. Okay, it can be 10, 20 or 30, whatever it is, this height actually represents that. So that is what basically normal distribution means. So in this world, most of the data would be normally distributed. Take the example of number of students studied in a particular village, completed 10th in a village with I mean, if you analyze the marks of the students in a particular village, most of the students' marks will be around 80 to 90 percentage. Only few students will achieve 100 percentage and only few students will fail. But most of the students will be around that mean 80 to 89 percentage or somewhere around. So getting less would be low, getting large will be low. So there will be slight deviations, but they all will be around the mean value, which would be around somewhere around 80 percentage. Students getting around 80 percentage with a standard deviation of 5, something like 75 to 85 would be more students. So that data is also normally distributed. Anything, shoe size of persons in a village, the foot size of the person. So most of them will have the common foot size somewhere around 6, 7. We only rare people will have um, 12 feet of shoe foot size, or some people will have very less foot size, something like 6. But most of the people will have the foot size around that mean, which is 5.5 to 6. So that is also normally distributed. So if the data, if the most of the data is spreading around the mean, we call the data as normally distributed data. We have a different slide for this as well, but this is just an initial understanding of what normally distribution is. Because you got this word here, standard deviation is used with the data which is normally distributed, and also where outliers are not a concern. Whereas mean absolute deviation is used where the outliers, where the data is less sensitive to outliers. With that, we should close going with more slides today. We completed 12 slides, and I strongly recommend to go through the slides again, and I'll also post the recording session to you. You can also use that for further reference.